Alright, good morning everyone. My name is Klenk. I'm a rising senior who attends McLean High School in Northern Virginia. And this summer at NASA Langley, I worked in the Systems Analysis and Concepts Directorate, specifically in the Vehicle Analysis branch. So first of all, I'd like to just introduce you to that directorate and that branch. So I'm going to read their mission statements to you. The System Analysis and Concepts Directorate, SACD, informs decision makers of the art of the possible. We can examine existing systems or define future architectures, vehicles, or operational concepts across the trade space within a physics-based, multidisciplinary, variable fidelity environment to determine the performance, cost, risk, and schedule feasibility and systems requirements to enable informed technical, programmatic, and budgetary decisions. From rockets to satellites, robotic precursors to human habitats, UAVs to commercial transports to hypersonic flight. From looking at the airspace we fly in to the air we breathe, SACD is helping NASA move forward. And the Vehicle Analysis branch. The VAB applies its multidisciplinary system-level expertise of high-speed atmospheric flight and end-to-end space transportation systems to connect appropriate technologies to innovative system solutions that enable Langley Research Center strategic thrusts to support NASA mission goals. We employ deterministic and probabilistic variable fidelity analyses, implementing empirical and physics-based methodologies in order to provide timely, insightful analysis and concept to flight. Okay, so before the days of powerful computers, CAD software, and computational fluid dynamics, if you wanted to test the aerodynamics of an aircraft or a spacecraft, you had to build a wind tunnel. And you had to model it, or draw it at least. You couldn't model it, really. You had to draw it, which required lots of skills to be learned, and you needed someone to model something, which required a lot of time and a lot of technical skills. Wind tunnels also are hard to operate, and you can only do one thing at a time. With the invention of powerful computers and CAD software, that process became a lot quicker and more streamlined. Nowadays at NASA, anybody can model an aircraft on their computer, and they can test it in the CFD program. So this summer I worked with OpenVSP, which is one of these programs. More standard CAD programs are made to design relatively anything, but OpenVSP is specifically designed for aircraft. Also, CAD and CFD programs are usually separate, and so that requires a bit of work to get a CAD file to work in a CFD program. OpenVSP has a simple CFD program built in to allow quick early air analysis of a model. So specifically, OpenVSP has these traits that make it helpful for aircraft design. It has quick modeling. It's very easy to build something quickly in OpenVSP, but it's also highly accurate if you want it to be. You can build very accurate aircraft. And so it's specifically made for aircraft design and, of course, the built-in CFD software. So design OpenVSP, how is that specifically made for aircraft? Well, first of all, you can right away, just by choosing what you want, say a wing, fuselage, or pod, create that. For example, on the right you see what you get if you just select wing, or on the bottom what you get if you select fuselage. And you can then modify these parts in different ways that are specific to how you would want to modify those parts. For example, for the wing, you can change the chord, the span, the angle of attack, you can change the shape of the airfoil, all sorts of stuff. And for the fuselage, you would change that in more conventional ways, length, width, height, all sorts of stuff like that. So that helps you model more quickly and more efficiently. But that also allows you to model very accurately. For example, for an airfoil, that's pretty difficult to model in a regular CAD program. But since it's specifically designed into OpenVSP, it makes it a lot easier, a lot more accurate, and also a lot quicker. Because of this, OpenVSP is actually also very intuitive and easy to learn. Because instead of having to learn a lot of unusual controls to get a roundabout, sort of long approach to get a shape you want, you just go straight ahead to that shape. And here are some of the controls that you can use in VSP. For example, on the top left there, you have the span, chord area, projected span. Those are all for wings. On the bottom left, you can move things in the X, Y, Z axes, and you can also rotate them. And there's all sorts of other controls that you have that once you learn them, they're very intuitive and very easy to use. Another great tool that comes with OpenVSP is the VSP Hanger, which is online and allows NASA workers to quickly share files between each other. And it also allows you to access files if you don't want to store them on your computer and take up a lot of space. So you can just go online to the VSP Hanger and load up these files onto your computer and do analysis on them. Or adjust them to make them more accurate, or just change them however you want. So VSP Aero. VSP Aero is the CFD program that's built into OpenVSP. It allows quick and simple aero analysis of an aircraft or just a simple part. It shows airflow lines coming off of an aircraft or anything off of surfaces. And it provides you with just a basic idea of the aerodynamics of a model before it can be tested in a specific CFD program more accurately, or in a wind tunnel even. And below you just see two examples of things tested in Open and VSP Aero. On the left you can see an aircraft, and you might see that the fuselage looks sort of like an extended bluff. That's just because in VSP Aero Viewer, everything's modeled in a sort of 2D thing, but the analysis actually is done on the 3D model. That's just for just helps the program run more quickly. There are, however, some issues with OpenVSP, with VSP Aero, and one of the things that I did this summer was I did some analysis on these issues, and I just found them because some of the developers of VSP Aero weren't aware of these issues. So some of the issues come in with vertical components, complex structures, and overlapping parts. For very simple vertical components, such as the one on the bottom right, VSP Aero will work, but for more complex ones, like on the left, which I'll talk to you more about in another slide, there are issues that arise. For the aircraft in the top right that I loaded from the VSP Hanger, the VSP Aero simply refuses to run it because it doesn't understand how to deal with some of the overlapping parts. What I mean by overlapping parts is that, for example, air intakes, you might want to model them as a cylinder, but part of that cylinder might be inside fuselage, and that's fine because that's a quick way to model it and it can be accurate. But VSP Aero gets confused with that sometimes. So I found these sort of issues and pointed them out. Also, sometimes with overly complex structures, like the aircraft in the middle, VSP Aero will run, but it will just be crazy. If you, for example, look at that aircraft in the center front on, you'll see that the airflow that models is not symmetrical on the left and right sides, and that's a good way to tell that there's definitely something wrong with that. So here's more in-depth view of the vertical, the issues with vertical components. So what I've modeled here is a model of, it's just a quick, simple sort of version of Formula One front wing with multiple elements and end plates, vertical end plates. And in the top left, we see the left half of that wing viewed from the rear in VSP Aero without that vertical element. And you can see two nice vortices coming off of the edges of the wings. And that's from higher pressure airflow on top of the wing, rolling off the sides of the wing and interacting and going down to the lower pressure air below the wing. And that reduces your wing efficiency and, in this case, the downforce that you're generating, which is something you don't want, which is why these vertical end plates are put there, because they keep the flow separate. However, if you see in the bottom left, it's kind of hard to see the vertical end plate that's there because it's just modeled in 2D again. But it's calculated for the 3D shape. You can see that VSP Aero is all sorts of confused with that. The vortice on the right side is still looking good, but on the left, well, it's pretty insane. There's two reasons sort of that's getting confused. First of all is the vertical component, and also the overlapping of the parts. Obviously, the elements of the wing wouldn't just be floating in space on a real Formula One car. They're attached to the vertical element, and I did that in the model, as you can see on the right. But it doesn't like that, VSP Aero. And so I showed these problems to the creators of OpenVSP and and so they can hopefully solve that problem in future versions. In the center there, I tried to sort of solve it by moving the end plates out a little bit so that the wing components are actually floating in space. But all that really does is create a sort of combination of the two on the left. You can see the vortices starting to form, but it's still all sorts of crazy because of the vertical end plate. And finally, another thing, another project that I did in OpenVSP was I recreated the HIMAT. The Rockwell RPRB H-70 HIMAT, highly maneuverable aircraft technology, was a NASA project that flew between 1979 and 1983 and was used to develop technologies for future fighter aircraft. The HIMAT was remotely piloted and featured an advanced 3D synthetic vision display. The aircraft was about half the size of an F-16, provided nearly twice the turning capability. At 25,000 feet and at 0.9 Mach, the HIMAT could sustain an 8G turn compared to the 4.5 of an F-16. So it's a very high-performance aircraft, and even though it's rather old now, its performance is obviously still really great, and that's why NASA is still interested in it and future versions of such aircraft. So what my goal was to accurately model this aircraft in OpenVSP. And so there it is. In the bottom right, we see a version that's just a grid skin. Helps you see see it more in the 3D view. You can understand scales and parts better. And the other two images are I've colored every separate component a different color to help me view it in that way when I was adjusting the sizes of different parts. And so some of the challenges that I faced when designing this were multiple overlapping components. For example, in the top right image, you can see that the fuselage is really made of three main parts. The top gray part is the canopy, the leading part of the fuselage, the more greenish part, air intake, and the rear part of the fuselage and the engine. And below the gold part is just a sort of bulge coming out of the bottom of the fuselage. That would have been very difficult to model using if I wanted to make it instead of the green part. But that is one of the reasons that this model does not work in VSP Aero, because the VSP Aero program does not understand which part of, say, the gold part of the fuselage and some other parts, how to model the airflow over that, because some of it obviously is inside the turquoise part of the fuselage, and some of it is on the outside, and it does not know how to differentiate between the two, and how to accurately model that. So that's a challenge for the developers of OpenVSP, and I relayed that and all the other issues that I found with VSP Aero to them in hopes of that they'll be able to improve and fix those issues in future versions of VSP Aero and OpenVSP in general. So my governor school experience, I had a ton of fun at governor school, both working at NASA Langley and through all the outside events that we did. NASA Langley is a fantastic place to work. I definitely experienced some of the issues that can come with working with a big government organization. We had some troubles with badge and pass and getting computers, but the rewards are definitely worth the drawbacks, in my opinion. And I think that my surviving the issues proved to me that without those issues, I would want to work in NASA even more. And it's really cemented my belief that NASA would be a great place for me to work in the future. And again, I had so much fun outside of NASA, fishing, the crab that scared us all, that we dug out. Yeah. So I'd just like to thank you to first of all, my mentor, Janet Ross. She was really great and very helpful, despite not knowing that she would be my mentor until five days before we started, I think, because of the issues with the one branch closing down or something like that. And I'd like to thank Dr. G for organizing this and for trying to control us all, at least trying. And Miss Becky for helping us with NASA, and I'd finally like to thank all you guys for making this such a great experience and for making this so fun. So thank you. And any questions? Yes.
Is OpenVSP a commercially marketed and available software, or is it just a NASA?
OpenVSP is available for everyone, yeah, so that's really useful, and it's a good tool for the public because it can be also used, I think, as an educational tool. So it's pretty easy to learn. Yeah, I think it's good. That's open to everyone. Yes.
You mentioned that VSP Aero got specifically confused by vertical endplates. Did other vertical parts of planes confuse it too? Like
yeah.
on tails sometimes?
Yeah, it was specifically, definitely vertical parts caused more issues than other parts. I'm not exactly sure why, but that was definitely noticeable. This very simple one that I showed you is just a wing with two vertical components on the end. I think VSP Aero, it was simple enough that VSP Aero understood what to do with that, and more simple that a design was that involved a vertical component, the more likely it was to get it correct. And that Formula One front wing was rather complex, and there's a lot of interaction between the vertical part and the more horizontal components that I think caused those issues. But it was definitely the vertical components that were definitely more noticeable for causing issues in VSP Aero.
Yes. In OpenVSP, the plane that's with made out of the blue lines, like the grid type thing, did you make that yourself, or how did you get that? Did you make it?
Yeah, so what I had was some pictures and a few dimensions of the high-mat aircraft. And OpenVSP has a really useful tool that allows you to impose an image on the sort of as a background, and you can sort of build off of that. And along with dimensions, that means you can build a very accurate aircraft. And with that, you sort of have to. It's kind of like Lego. You really have to. Say someone dumps a bucket of Lego in front of you and says build a plane. You can probably build a plane in a lot of different ways, and you can do that in VSP Aero. You can probably make something in a lot of different ways. For example, let's go back to that. See all these components? You can probably do that in a lot of different ways, but you just have to come up with a way that works, and that's sort of a challenge in it. But I think it's a very fun one, and one that I really enjoy doing. You have to come up with going way to create that design in the software.
So I noticed on one slide you had like a bunch of the sliders that like adjust the like degrees of things. Is that right? Yeah, those right there. Wait, so if you like were to adjust those, would it like adjust the degrees of like the wings and stuff on the plane that you made yourself?
Yeah.
Like, could you slightly modify it?
Yeah.
Okay,
Yeah.
you could. Okay.
Yeah, for example, take that wing over there. If I say span, I increase the span, I can type in a number or I can just move the slider. The span will increase, the length of the wing basically, or will increase the width of the wing at the base. And yeah, there's all sorts of settings that you can do that will change that. So you can plug in accurate values that you know that are exact, or you can just sort of roughly guesstimate depending on what level of detail you want.
Okay, cool.
Yes?
So, thinking about your experience this summer, 10 years, where do you see yourself 10 years from now?
10 years, I'll be 27. Wow. 27, I'll probably be doing like maybe a PhD or something like that. Definitely in an area related to what I've been doing at NASA. Yeah, I mean, as I said, I was probably one of the people who got hit the hardest with some of the issues that can come up. But really, this has been such a great experience, and I've really, as I said, it's just cemented my belief that this is the area that I want to go into. So in 10 years, definitely, I don't know exactly where or exactly what, but definitely aerospace for me. Yeah. Okay. Thank you.